So this is going to be a quick overview of the playlist which discusses how mammals evolved. The idea that mammals could evolve on the face of it seems, well, ridiculous actually, because when you look at the animals alive today, mammals don't remind us of reptiles at all. I mean, deer don't remind us of snakes, and dogs don't remind us of turtles. And crocodiles don't remind us of people or rodents. So there seems to be this huge gap between mammals and reptiles, which is the closest amniote group to mammals. So how on earth, can we even start this conversation? Well, the reality is that while what I said is true, there is great differences between modern reptiles and modern mammals. It is different from the situation which existed 200 and some million years ago in the Triassic period, because at that point there were mammals which were almost reptiles, and reptiles which were almost mammals. And so the question is not whether snakes evolved into deer, which they obviously didn't, or turtles evolved into rodents, which they obviously didn't. But did the Triassic reptiles, which were very similar to mammals, did they evolve into the Triassic mammals, which were very similar to reptiles? And so the discussion then has to begin with a group of fossil reptiles that most people don't know very much about, the synapsid reptiles. And so what we're going to have to look at is whether over tens of millions of years, well over 100 million years, there was a gradual set of changes between pelycosaur reptiles, which were reptiles with a few mammalian features. Did they evolve into therapsids, which were reptiles which had significant mammalian features? Did they evolve then into cynodonts, which were mostly mammal, but still reptilian? And so that is what this playlist addresses. It looks at the pelycosaur reptiles, the therapsid reptiles, which, I'm sorry, let's do this in order. The pelycosaur reptiles, this is the most primitive group, which begin in the Carboniferous period. And then the therapsid reptiles, which then start at the end of that begin in the Permian period and last into the Triassic, and then the cynodonts, which begin at the latest Permian and then last into the Triassic and beyond, the Triassic period being when the first mammals appeared. This is quite a significant amount of time in history. So we're looking at the mid-Carboniferous period, when the first synapsid reptiles appeared, through the Permian, through most of the Triassic, which is well over 100 million years. And so in this playlist, I start off with just an introduction into the pelycosaur reptiles. Pelycosaurs were the most primitive synapsid reptiles. This is the group of reptiles which share the features of a single temporal opening in the skull, as discussed earlier. If you don't have an opening in the skull here, your jaw muscles can only be this long. And with short jaw muscles, then one doesn't have that powerful a bite. But the more advanced reptiles evolved openings through which the muscles which attach to the lower jaw, can then pass through, be longer, and have a more powerful bite. Mammals have one single opening, and these synapsid reptiles have that one single opening like modern mammals. So here are reptiles with a mammalian trait. While most reptiles have only one type of tooth, for example, in crocodiles, all of the teeth are sharp and pointy, and there's really no distinction between the kinds of teeth. Here, there was a distinction between the cheek teeth starting to be a bit different from the teeth up in front, with a prominent tooth in this area, which would be the homologue of the canines, which is a feature of mammals, something that no reptiles have. So this pelycosaur reptile was starting to show mammalian features. Now, should you be impressed? Well, perhaps not at this case, because it's mostly reptilian. It doesn't separate its oral and nasal cavity the way that mammals do. It has a small reptilian brain. It still has an opening between the parietal bones for the pineal foramen, which is a reptilian feature. Its skull is mostly reptilian, although it does slope a little bit in the occipital region. This is more of a mammalian feature. And so its skull includes bones, which mammals lack today, but which reptiles have. So its skull was a mix of features with some mammalian features, but primarily being a primitive reptilian skull. Its posture was certainly reptilian. It did not hold its body off of the ground. It was sprawling. It had a long reptilian tail. It still had ribs in the cervical region and in the lumbar region. These are reptilian features. And so these are certainly not mammals. These are reptiles, but they are reptiles which start to show mammalian features. And this then is the question: could mammalness evolve in gradual stages? Could there be transitional forms? And these pelycosaurs show just that. They show reptiles or animals which are mostly reptilian, but which have a few mammalian features. So they have some, but not all of the features of mammals. And they have some, but not all of the features of the next group of synapsid reptiles. Now, these pelycosaurs were quite successful in their day, because in the Carboniferous going into the Permian period, there were no dinosaurs, there were no crocodiles, there were no mammals. And so therefore, many of the successful groups which would appear later simply weren't around. So some of these were small insect-eating forms, but some of these could be 10 feet long, eating meat, or even longer, more than 15 feet long, eating plants. So because they spread all throughout the world, there were plant eaters, there were carnivores, there were small insect eaters, etc. Now, it is significant that it was the reptiles which had figured out that one could eat plants. The amphibians, they never really did that. And once you figured out that you could eat plants, obviously today we know that you can become quite large eating the green stuff. And so some of these pelycosaurs, they became quite large, and there were no modern herbivores that they were competing with. They were early animals to adapt to this lifestyle. You can see here in both the carnivorous Dimetrodon and in the herbivorous Edaphosaurus, these elongated vertebrae, which would have created sails. Among other things, this would have allowed them to control their body temperature to a better degree. If they could turn into the sun, they could warm faster. If the wind was blowing, they could cool faster, depending on how they oriented their body. And so we know that mammals take very seriously the control of body temperature. Their metabolism depends on their ability to control their body temperature. These reptiles apparently were taking steps in that it was obviously important to control their body temperature if they had gone to the extent of getting this sail, which would allow them to do that. So pelycosaurs were very successful reptiles starting in the mid-Carboniferous. This form was originally classified as a pelycosaur. Now it's classified as a THERAPSID, a more advanced group, which is closely allied to the pelycosaurs. And so from the primitive pelycosaurs, a more advanced group of synapsid reptiles evolved, known as the THERAPSIDs. These THERAPSIDs, sometimes called the saber-toothed reptiles, many of them had prominent canines. Once again, that's not a modern reptilian feature. That is a feature of mammals. These therapsids were still reptiles, but nevertheless, they had the synapsid opening. They were modifying their teeth and lower jaws. I'll get to the lower jaw in a little bit. And they formed a number of groups. While the first pelycosaurs were carnivorous and they adapted to both herbivorous and carnivorous lifestyles, the first therapsids were carnivorous, but they adapted to both carnivorous and herbivorous lifestyles. They began to hold their bodies more erect. Their bellies did not drag on the ground, although their arms and legs probably would have at first gone out to the side a bit more and not been completely held underneath the body. Now, they would last during the Permian period. Some would actually survive the mass extinction at the end of the Permian and go into the Triassic period, like Lystrosaurus. Lystrosaurus at the beginning of the Triassic might have been one of the most common organisms on Earth because at this point all of the continents were fused, and Lystrosaurus was able then to travel throughout the continents of the world. Many of these therapsids were herbivores, like the ones you're seeing here. These tusks that you're seeing, they would not necessarily have been to help them feed, unless it helped them to dig up roots and the like, and probably more for defense or for combat in their own species. But in addition to the herbivores, there were a number of carnivorous groups. Now, keep in mind, these are still reptiles, and you can see that they still have a small tubular brain. They still have neck ribs that the mammals would lack. They still have ribs in the lower back, the lumbar ribs. Their arms, at least, are still sprawled out to the side to a bit, but they are not dragging their bellies on the ground. And look at this iliac crest. More significant muscles are coming from the leg region because they start to change the way that they move. Reptiles tend to move their vertebral column a great deal, the same way that fish do. When fish swim, they're swimming in this S-shaped pattern. When the first tetrapods made it out on the land, they did the same. So think of a salamander or a lizard. It's using its back to a great degree to move forward. The arms and legs are more just to hold on to a place so that now these strong back muscles have something to push off against. These therapsids started to change the nature of their back vertebrae so that their back would move less and got larger limb muscles. So they were depending more and more on muscles in the arms and legs and more on keeping their backs straight. So they were starting to move more like mammals would. Warm-blooded animals tend to have more openings in their bones, more holes for blood vessels, and we see what we think then is evidence of being warm-blooded in these therapsids. Their bones have significantly more holes for blood vessels. And so while these are reptiles, it seems that they are on their way to being warm-blooded as something that we associate with mammals. And so once again, these are transitional forms. They have some, but not all of the features of mammals. And these transitions are occurring in order. So these have more mammalian features than the pelycosaurs, which came before them, but not as many as would be held by the cynodonts, which come after them. There were many groups here. This animal might look a bit dog-like, but it's still a therapsid reptile. So it's a reptile. But once again, when we look at the way it holds its body and other features, perhaps being warm-blooded, its partially reduced tail, it is certainly on the way to becoming more mammalian, but it still has the smaller brain, the cervical and the lumbar ribs, the partially sprawled forearms, which mean that it's not quite a mammalian. And so if we were to put these lineages in order, the pelycosaurs would be the most primitive, and then the therapsids, the second a group. And if you were looking for, something that might be, say, 50-50, half, reptile, half mammal, these therapsids, such as these gorgonopsids, they would, certainly be likely candidates. They certainly had a number of primitive features which the ancestral reptiles possessed, but then they also then had advanced features which ancestral reptiles lacked, but which mammals possessed. From the therapsids, then a third group of reptiles evolved, the cynodonts. The first cynodonts are known from the end of the Permian, and while these were more advanced than therapsids, they were more primitive than the cynodonts, which would come later. They have extra teeth lacking in the later ones. They have two vomer bones, the later ones would have one, and they lack a secondary palate, which I will define in just in the next video. So by the time the Triassic period begins, the cynodonts are a bit more advanced. Notice they've lost their ribs in the lumbar region. That's extremely significant for breathing, as we will see. Now, these are still reptiles. They have all of these reptilian features like cervical ribs, a reptilian jaw joint, which I'll get into in a little bit, primitive components of vertebrae, but they are now much more advanced as well in these features, with their body being held more erect, larger limb muscles, with the ilium larger, the pubis smaller than other reptiles. So if you were to look at the skull of cynodonts, clearly there are still some reptilian features. You still have this pair of bones. This bone and this bone, which the mammal lineage will lose. Their brain is still not as large as it will be later. But then there are plenty of other changes. So for example, the lacrimal bone is becoming shorter, no longer extending to the tip of the snout, as was the ancestral condition. As I'll discuss in just a little bit, they were beginning to modify their cheek teeth for chewing. In later lineages, the hole between the parietal bones for the pineal foramen would be lost, and they would have two occipital condyles, where the ancestral reptiles simply had one. Now, let me just step backwards and explain why some of those changes were significant. It does not take that much energy to run a frog or a turtle. And so, although a frog has separate nostrils and a mouth, notice where the nostrils empty into. They empty into this one space. So frogs don't have a separation between the oral cavity and the nasal cavity. It's just one space. The nostrils come in right here. And so if you're a frog, you can't breathe and eat. You have to make a choice. If you have one space, you can only do one thing with it. And the same thing, the nostrils of the turtle and empty into the same cavity that the mouth does. There isn't what's called a palate. Now, that isn't that big a problem for a turtle. I mean, it can either have air in this area or food, but turtles don't have to breathe that much, nor do they have to eat that much. So they can stop eating to breathe, and and vice versa. Mammals, however, simply can't do that. Mammals are expensive, and so the only way that a mammal can maintain its high metabolism if it's breathing far more than reptiles do and eating far more than reptiles do. And so mammals can't afford to cut back on eating or breathing so that they can do the other feature. And so what allows them to do this is that bones in the roof of the mouth fuse together to form a hard palate. The maxillary and palatine bones come together so that the nasal cavity is now separate from the oral cavity, and they can eat and breathe at the same time. Now, while today we associate that with mammals, it was the cynodont reptiles which evolved this trait. So once again, they were becoming mammalian. So humans have a separation between their oral and nasal cavities, as do all mammals. Notice this hard palate. This hard palate, the nostrils and the nasal cavity are in that area. So these cynodont reptiles, they were the ones which divided the oral and nasal cavities, and this allowed for the higher metabolisms of mammals later. Once again, mammals are very expensive, and the only way that they can accommodate, being warm-blooded, which is expensive, and having a big brain, which is expensive, and walking upright and not dragging their bellies on the ground is expensive, is to get more energy from their food. So mammals chew their food, something that most animals simply do. So notice this great blue heron. It isn't chewing that catfish. Notice this condor. It's not chewing. That they just chomp, chomp, and swallow. Now, if this is inefficient, if these animals don't get all of the energy out of the food, well, it doesn't quite matter because, for example, a zoo can typically keep 40 big crocodiles on the same amount of food as one tiger. Crocodile bodies just aren't as expensive. And so if the crocodile is a bit less efficient, that isn't the end of the world. Mammals, however, the only way that they can maintain that expensive, body temperature, a large brain, and upright stance is to be much more efficient. So unlike most animals, mammals will have cheeks. Notice that these animals don't have cheeks. The teeth are right at the edge of the jawline, and they have different kinds of teeth. So because they have cheeks, they can hold food between their teeth and their mouth and then push it around with their muscular tongue, something that most animals don't do. And if you look at the cheek teeth have a number of features. One, they touch each other when the jaws are closed. That's something that most vertebrates don't have. The teeth don't touch each other. And not only do they touch each other, they have matching surfaces. This is known as occlusion. And so mammals can efficiently tear up their food, making more of the nutrients in that food available because their teeth contact each other and they have these matching surfaces, this occlusion, which allows them to rip food apart. But while this is today a mammalian feature, it was the cynodont reptiles which were modifying their cheek teeth so that they would contact each other and then have matching surfaces. So once again, today the mammals are making use of features which evolved in their cynodont reptilian ancestors. By the time you get to the mid to late Triassic, there are cynodont reptiles which are so similar to mammals that experts could argue as to, are these, fully reptile? Are they fully mammal? Where is the reptile mammal line? And, some have said, while, some experts classify, say, one organism as a mammal, others say, let's call that a mammaliform, an almost mammal. And so while today there's really no confusing a reptile and a mammal, in the Triassic period, that wasn't the case. The advanced cynodonts were very mammalian. Some of them even lost those two bones which made up the post-orbital bar. So notice here's a cynodont reptile. It has lost these two small bones which ancestral reptiles had, forming a post-orbital bar. The cynodont reptiles lost it, and none of the early mammals would have this post-orbital bar. The mammals, which later get a post-orbital bar, they get that back in gradual stages. What does all this mean? Well, just to sum all of, I'm sorry, I forgot one feature. Well, okay, we'll see it here. Mammals are hotter, smarter, and faster than reptiles. All right. So if you look at these changes which occurred as one, went from the pelycosaurs to the therapsids to the cynodonts in more than 100 million years, by the time you get to the end of that chain, they are hotter, and by that I mean they're warm-blooded. The therapsids seem to have been warm-blooded by the number of holes in their bones. And then the cynodonts seem to have more blood vessels and padding in this area of the snout, which suggests that they had whiskers. So we think that hair and warm-bloodedness had evolved by this point. And certainly we could see that the pelycosaurs, with their sails, they had placed an importance on regulating their temperature. And so they are hotter than their ancestors were. The brain is larger than the ancestral brains were, and brains are very expensive. And then if you look at their body position, they're holding their bodies more upright, not dragging their bellies on the ground. They have larger limb muscles. See how big this ilium is for the leg muscles to attach. So they are hotter, they are hotter, they are smarter, and they are faster. So here you see just a thermal camera of people. So while there are advantages to all of those traits, there is the disadvantage. This is expensive. If you're constantly going to be hotter than your environment, if you're going to be 100 degrees in February, that's expensive. You're going to have to pay for that. If your brain is big, brains are extremely expensive. Your brain makes up 5% of your body's energy, but uses almost, or I'm sorry, 5% of your body's weight, but uses almost 20% of your body's energy. Brains are very expensive. Holding your, not dragging your belly on the ground to move, that is very expensive. So how do you pay for it? Well, look at this mouse and look how fast it's breathing. All right. Reptiles don't have to breathe this fast. They don't need that much oxygen. All right. But mammals do, because if you're going to have a warm-blooded metabolism, a larger brain, and be faster, you need to be able to power that. And so we see that certain things evolved over reptiles. The therapsids did not have a hard palate, but the cynodonts evolved this trait so that now they could breathe constantly, even when there was food in the mouth. The therapsids still had lumbar ribs, but the cynodonts would lose that feature. So lumbar ribs was an ancestral feature, but the cynodonts, they lose the ribs in their lower back here. Why is that significant? Well, because mammals have a muscle which all other vertebrates lack, called the diaphragm. The diaphragm pushes down on the abdominal guts when we breathe so that our guts hang out, but that our lungs get longer. So if you were to just stand in front of a mirror and then let your guts hang out and suck them in, let your guts hang out and suck them in, you might notice that your ribs aren't moving when you do this, but you're breathing. So I can breathe just fine without moving my ribs at all, as long as my guts hang out and then come back in. And this is because mammals have this diaphragm muscle, which pushes down on their guts, and their guts hang out. All right, well, why would you want your guts to hang out? Well, when they do, your lungs are getting longer. So mammals can take in more oxygen in each breath than a reptile can. And so mammals with their larger brain, warm-blooded metabolism, and greater mobility can now bring in more oxygen to power that. They can process their food more efficiently. So their mouth is going to actually serve as a functional digestive organ. They have cheeks to hold their food in their mouth. They have different kinds of teeth, including teeth with occlusion, matching surfaces, which can then rip the food apart to make the nutrients more available. And so it was the Pelycosaur, Pelycosaur therapsid, and cynodont reptiles, which evolved these features which allowed mammals to be mammals. Mammals can only have their warm-blooded metabolism, big brains, and better mobility if they can pay for it. And it was these reptiles which slowly developed the ability to bring in more oxygen with the palate and the diaphragm and the loss of the lumbar ribs to better get energy from their food with their occlusion, to better be able to move by making their back more solid and making their limb muscles larger. And so while today reptiles are so very, very different from mammals, it should then be remembered that the evolution of mammals from the first synapsid reptiles took more than 100 million years, among the synapsid reptiles, which were among the most common reptiles on Earth. So over 100 million years, the primitive pelycosaurs became therapsids, which then became cynodonts. And then by the late Triassic, these cynodont reptiles are so similar to mammals, or the Triassic mammals, that it is actually hard to tell them apart. Now, before talking about the first mammals in the next video, I would like to just make two final comments on things that had occurred during this transition. One is, if you were to compare the skull of a mammal and a skull of a reptile, one of the things that leaps out is that mammals have big bones where reptiles have lots of little bones. So mammals have a big occipital bone here. Mammals have a big temporal bone. Mammals have one single frontal bone as opposed to two, while reptiles have lots of little bones. So how did that happen? Well, over these tens of millions of years, as pelycosaurs became therapsids, which became cynodonts, a lot of small bones then fused to make bigger bones. And so a lot of the single large mammalian bones are what we call composite bones. Composite bones, which actually formed from taking a number of small bones and smushing them together. Now, one can not only see that in the fossil record that gradually occurs, but if you were to say take a modern human or a modern mammal, in embryos there isn't an occipital bone, all right, but there are all of these little pieces which match the little bones that reptiles used to have, and that just as over the evolution of these mammal ancestors, these little bones fused together. In embryos, including human embryos, these little bones fuse together to make then the solid composite bones. So the occipital bone forms from many separate centers, and human fetuses have a basio-occipital and exo-occipitals, just like mammal ancestors had separate basio-occipitals and exo-occipitals, which then fused together. The same is true of the temporal bone. The same is true of the sphenoid bone. Mammals today have one solid bone, but while reptiles had lots of little bones. But now in what we see in both the evolution of mammals and in mammalian embryos is lots of little bones come together to fuse the solid composite bones. Two frontal bones, fuse to make one frontal bone. Two vomers fuse to make one vomer. The premaxillary, which holds the incisors, fuses to the maxillary, which holds the rest of the teeth. So this is where the composite bones of mammals come from. The very last topic I'd like to mention is the evolution of the lower jaw. Now, the evolution of the lower jaw doesn't sound that exciting, but it actually is. The ancestral condition in fish, amphibians, and reptiles was not one single bone of the lower jaw, which mammals have today. We call this the dentary, nor was it having the dentary of the lower jaw touch the squamous portion of the temporal bone in the upper jaw for the jaw joint. So all mammals today have a jaw joint where the dentary touches the squamosal part of the temporal bone. It's called a dentary squamosal jaw joint. Fish, amphibians, and reptiles, they have more different bones in their lower jaw, and they have a different jaw joint, not a dentary squamosal jaw joint, but rather a quadrate articular jaw joint. If we could take the bones of the amphibian and fish and reptilian lower jaws and label them, here all they are, we're going to see this change as mammals evolved. A couple things to watch. One, the blue bone, the dentary, will get bigger and bigger until it is the only bone which remains. And these yellow bones would have been part of the upper jaw area in this region of the skull. So the jaw joint occurs between the yellow bones and the red bones. So the ancestral jaw joint was a quadrate articular, the red bone being the articular, the yellow is the quadrate. A quadrate articular jaw joint instead of a dentary squamosal. Well, as fish evolved into amphibians, which evolved into the first reptiles, the blue bone got bigger and these other bones got then smaller. As we then go into the pelycosaurs, into the THERAPSIDs, the pink bone gets a hook in it. That's interesting. We'll get back to that later. And while the jaw joint is still between the red bone and the yellow bones, the red bones and the yellow bones are getting smaller. On the medial surface of the lower jaw, there ends up being this little bar of these little bones which remain. By the time you're getting into the cynodont reptiles, the blue dentary bone makes up most of the lower jaw, and these animals are starting to adapt to chewing. All right, and so therefore they need bigger muscles, and you see bigger muscle attachments here. The pink bone's getting a hook in it. We'll get back to that. We still have this bar here. And while these bones still touch each other, the blue dentary bone begins to make contact with the squamous portion of the temporal bone. And so these reptiles had two jaw joints, the ancestral reptilian joint, which was on its way out, and the new mammalian joint, which was on its way in. And so these are transitional forms with two jaw joints next to each other. By the time you're getting to the advanced cynodonts, we now look like this. Now, while this bar will eventually disappear here, this was, partially present in some early mammals and in modern mammalian embryos, including human embryos. There is a bar of cartilage which forms in that position, known as Meckel's cartilage. As we make the transition into the first mammals, the pink, the red bones, and the yellow bones are no longer incorporated into the jaw, and so now the jaw is just the blue bone. So while mammal jaws are made of one single bone, it took a while to get to that point. Well, what happened with these small bones here? Well, if you look here at this human skull, you can see that the lower jaw is made of one bone only, and the jaw joint is the dentary squamosal, a jaw joint between the dentary bone and the squamous portion of the temporal bone. Notice that right behind that, there's a hole in the temporal bone that has little bones in it. So the temporal bone actually has little bones inside a cavity, all right? These small bones are auditory ossicles, and the yellow and red bones from the previous animation, they became modified to become the malleus and the incus. The stapes was an older bone that reptiles had as well. So mammals are better able to hear than reptiles were, in part because they have these two small auditory ossicles in addition to the one ancestral one, which then gets modified to amplify sound. If you were to examine a fetal skull, you can note that just behind the jaw, you see these little bones. You see the malleus and incus, which are the homologs of the quadrate and articular, the yellow and red bones. But also notice this bone that supports the eardrum, forming a ring. That's the homolog of the pink angular bone. And so the mammalian middle ear modified ancestral jaw bones, which were no longer needed in jaws as mammals modified their lower jaw. In modern marsupials, these bones associate with the jaw at birth, but while they are maturing in the pouch, they become incorporated into the ear. And so it is a wonderful story of how reptiles evolved into mammals, but it is a slow, gradual story. It occurred over 100 million years, from the late Carboniferous with the first synapsids to the THERAPSIDs of the Permian to the cynodonts of the Triassic, before the very first mammals of the late Triassic had evolved. And the features of the first mammals evolved slowly through gradual stages in reptiles which had some, but not all, of the features of these mammals.